for which what we do, we prepare a small scale models in the laboratory and we conduct various tests on this model in the laboratory to study the performance of that structure, of that model. If the model is doing good and giving good performance at so and so dimensions, at so and so parameters, then we try to transfer these parameters to the actual structure which is going to be constructed in the field, which is a prototype structure. So what we try to do is we prepare a model in the laboratory, conduct various tests on it, arrive at the best performance for the model, transfer these parameters using these similarity laws to the actual structure. For example, if you have to construct a spillway, I don't construct a spillway directly in the field. What we do, we prepare a small spillway model in the laboratory, conduct several tests there, study the performance of this model. If the performance is not good for the model, you will be able to change the dimensions easily, but for the actual structure, you will not be able to change the dimensions of the actual structure. So it becomes a very costly affair. Sometimes it cannot be done also. So that is the reason why a hydraulic engineer, a civil engineer, is more interested to see that a model is prepared and this model will be studied. After arriving at the best performance for the model, these parameters of the model will be transferred to the actual structure which is going to be constructed in the field by making use of the similarity laws like geometric similarity, kinematic similarity, and the dynamic similarity. That is the reason we study about the model and the prototype relations also. I hope you are now very clear what is the need of studying this unit by a civil engineer. We need to study because we cannot afford to construct a big dam of 100 meters high and tomorrow you say that no, it should have been only 80 meters. I want to cut down. We cannot afford that because it's all thousands of crores of rupees. Okay, so that is the reason we try to prepare a model, study on the model, and arrive at the performance, then transfer to the actual structure. Okay, model prototype relations. Distorted, non-distorted. As the process goes on, we try to understand what is this distorted, non-distorted. Okay, so we have dimensional analysis techniques like Rayleigh's method and Buckingham Pi method, followed by the model analysis for the hydraulic structures. Both the things we will see in this important unit. Okay, dimensional analysis is a mathematical technique for the solution of several engineering problems. We know any other fluid flow problem, more particular to the fluid mechanics, if I say, any other fluid flow problem can definitely be solved by making use of the very conventional procedure. Apart from that conventional procedure also, we will be able to solve the same problem by making use of these mathematical techniques. To quote a small example, if I say that flow through an orifice, we know very well to get the discharge through an orifice, we try to understand what is the orifice, a small opening provided by the side of a tank, and when the flow is taking place through this orifice, what are the various parameters which may be influencing, and based on which we try to apply the momentum equation, apply the energy equation, apply the continuity equation, and try to get the solution for the discharge equation. Q is equal to CD into small a into square root of 2G H, which you already studied in your earlier fluid mechanics. Q, the discharge, CD, coefficient of discharge, small a, the cross-sectional area of the orifice opening, G, acceleration due to gravity at that location, and H is the head over the orifice. Okay, so this equation can be solved by making use of the conventional procedure like momentum equation, continuity equation, and so on. Apart from that, the same equation can be solved, or the same problem can be solved by making use of the mathematical technique dimensional analysis. Okay, so the logic behind that is each physical phenomenon can be expressed by an equation composed of the variables or physical quantities, which may be either dimensional or non-dimensional quantities. Any physical phenomenon can be expressed by an equation. Okay, so this equation we are having several physical quantities. These physical quantities may be, some may be dimensional, some may be non-dimensional also. So to carry out this, we take the fundamental quantities. These fundamental quantities also are called primary quantities. So the various physical quantities used by the engineers to describe a given phenomenon, which can be described by a set of quantities. For example, mass, length, and time are considered to be the fundamental quantities in the Mld system. Of course, wherever there is a variation in the temperature, theta also is required to be considered. Theta also is required to be considered. Wherever there is a change in temperature, mostly as a civil engineer, we concentrate on incompressible fluid flows. Since the fluid is incompressible, temperature will not be varying, and hence we have three primary or fundamental quantities: mass, length, and time. Okay, these three are considered to be the primary quantities. Wherever there is a variation in the temperature by compressible fluid flow analysis, etc., you need to take temperature theta also as one of the primary quantities. Apart from this primary or fundamental quantities, we have derived quantity. What is this derived quantity? Any other quantity, if you take, say, area, this can be expressed in terms of the primary quantities. This can be expressed in terms of the primary quantity. All such quantities are called the derived quantities. Area, volume, velocity, acceleration, force, energy, power, all these are with the derived quantities. Whereas MLT, mass, length, time, are considered to be the fundamental quantities. So the expression for a derived quantity in terms of the primary quantities is called the dimension of the physical quantity. For example, if I take force, what is force? Mass times acceleration. Mass times acceleration. Mass is m. What is acceleration? Acceleration is Lt to the power minus 2. So m into L into t to the power minus 2 would be the force. So any other quantity other than mass, length, time can be expressed in terms of the derived quantities. For example, if I take force, the dimensional formula for force will be mass into acceleration, mass m into acceleration meter per second square, Lt to the power minus 2. So force will be having a dimensional formula of ml t to the power minus 2. We have another system also, like FLT system. This is what we adopt is MLT system, where mass is considered to be the primary quantity, fundamental quantity. But we have another system known as the FLT system, where force is considered to be the primary quantity and mass becomes a derived quantity from which you will be able to derive the dimensions in terms of F, L, and T. But of course, we adopt only MLT system. We adopt only MLT system. What is dimensional homogeneity? What do you mean by an equation being dimensionally homogeneous or dimensionally non-homogeneous? It all related to the dimensional formula of all the terms involved in the left-hand side of the equation to the right-hand side of the equation. So, if the dimension formula of the left-hand side is equal to the dimensional formula of the right-hand side of a given equation, then we say that it is a dimensionally homogeneous equation. Dimensionally homogeneous equation or dimensional homogeneity, which states that the dimensional formula of the left-hand side of a given equation is equal to the dimensional formula of the right-hand side of the given equation. Then we say that it is a dimensionally homogeneous equation. Take an example like discharge through a rectangular weir or a notch. Rectangular weir or notch. Because I'm making use of these examples, your valuers, you already used these equations and derived these equations, applied these equations in your fluid mechanics subject in the earlier course. So the equation for the discharge Q would be equal to 2 by 3 CD root 2G L H to the power 3 by 2. You know very well what is a weir, what is a notch, right? Rectangular notch, triangular notch, trapezoidal notch, several types of stipulative weir. Those things you already studied, right? So the discharge Q over this rectangular weir or a notch would be 2/3 CD root 2G L H to the power 3 by 2. CD coefficient of discharge, G acceleration due to gravity, L is the length of the crest, and H is the head over the weir or notch, which is causing flow. So how do you say that whether this equation is dimensionally homogeneous or not? Simply take left hand side, write the dimensional formula. Right hand side, write the dimensional formula. If both are same, dimensional formula of left hand side is equal to the dimensional formula of right hand side, then we say that the equation is dimensionally homogeneous. Just start writing. Take left hand side Q, discharge, meter cube per second. Discharge is rate of flow, volume rate of flow, volume by time, meter cube per second. So cube by t, or L cube t to the power minus 1. This is the dimension formula on the left hand side. Similarly, for the right hand side, if you see 2/3, CD, √2, all these are the constants. So for a constant, the dimensions are m to the power 0, L to the power 0, t power 0 into root g acceleration due to gravity, Lt to the power minus 2 to the power half, because it is under root, into L is the length of the crest. So it is, once again, the dimension formula L. H to the power 3 by 2. H is head. Once again, a linear dimension. So dimension formula is L to the power 3 by 2. So if you simplify all the right hand side, you have m to the power 0 anyway. L to the power half here, L to the power 3 by 2. So your total L cube. Similarly, t to the power minus 1, and there is no other word. There is no other term. So your L cube t to the power minus 1 is the dimensional formula for the right hand side of the equation. Left hand side, L cube t to the power minus 1. Right hand side, L cube t to the power minus 1, which indicates that the given equation is dimensionally homogeneous equation. You may have dimensionally non-homogeneous equations also. For example, if you take Manning's equation, V is equal to 1 by n, r power 2/3 s power half. 1 by n, r power 2/3 s power half. So in this equation, you may observe that V, the velocity, Lt to the power minus 1. On the right hand side, slope anyway, there is a gradient, no dimension for it. R, hydraulic radius, L. So you have L to the power 2 by 3 here. On this side, you have Lt to the power minus 1. So this is a dimensionally non-homogeneous equation, because left hand side, right hand side are not equal. So what is happening in such equations? Because it is dimensionally non-homogeneous equation, you need to be very specific in applying the unit system. So if I give some value, if I assign some value for n, this n value may be applicable provided the equation is implemented and applied in that specific system of units only. For example, if I say metric system of units, n is 0.015, which means that the velocity v must be substituted in meter per second. The hydraulic radius r must be substituted only in meter. Then only the value of n is equal to 0.015 can be applied. So this is dimensionally non-homogeneous. In a nutshell, to say dimensional homogeneity refers to whether the given equation is dimensionally homogeneous or non-homogeneous. A dimensionally homogeneous equation is the one in which the left-hand side dimensional formula is equal to the dimensional formula of all the parameters available on the right-hand side of the equation. If they are equal, dimensionally homogeneous equation. If they are not equal, it is dimensionally non-homogeneous equation. If we take Cauchy's formula, so these are all very semi-empirical formulae. So V is equal to C into square root of RS. V is equal to C into square root of RS. So if you, unless you give a certain dimension for C there, it cannot be dimensionally homogeneous. The moment you start giving the dimension for the coefficients, like Manning's coefficient or Cauchy's coefficient, the equation would be the specific system of unit specific. If you are using MK system, or if you are using, say, FPS system, accordingly the value of n, the value of C would be changing. That is what is dimensionally non-homogeneous. Having understood about the dimensional homogeneity, let us try to see what are the methods which are there for analyzing the to get the mathematical solution for the fluid flow problems. Rayleigh's method, Buckingham pi method. There are two methods through which each method is having its own advantages compared to the other method. So we discuss both the methods and we try to see what are the relative merits and demerits of both the methods also. Okay, let us take the Rayleigh's method. This method of dimensional analysis was proposed for determining the effect of temperature on the viscosity of a gas. In this method, a functional relationship of some other variables is expressed in the form of an exponential equation, which must be dimensionally homogeneous. So there are two terms that we have been using here. Functional relationship. That means you may identify in any physical phenomena, you may identify some variables as independent variables, some variable as dependent variables. So you need to identify the dependent variables and the independent variables available in a physical phenomena. Then you will be able to establish a functional relationship between the dependent variable and the independent variable. So this functional relationship between the dependent and independent variables in a physical phenomena can be expressed in the form of an exponential equation by making use of this Rayleigh's method. And we assume that this exponential equation is dimensionally homogeneous. This exponential equation is dimensionally homogeneous. I repeat once again about this method. In the Rayleigh's method, we try to identify the dependent and independent variables involved in a given physical phenomena. Once you establish the functional relationship between the dependent and independent variables, then we'll be able to express an exponential equation by making use of this Rayleigh's method between the dependent and independent variables. And we assume that this exponential equation is dimensionally homogeneous. If you start solving this exponential equation, we will be able to establish the relation between the dependent and independent variables. Okay. So if we take x is a dependent variable, which is function of or which is depending on several independent variables like x1, x2, x3, and so on, xn. So what is x? X is a dependent variable. x1, x2, x3, so on, xn are the independent variables. So the relation between the dependent and independent variables may be expressed as a functional relation, also as exponential relation using Rayleigh's method. Let us take up the functional relation. The functional relation is so simple, like x is equal to function of f of x1, comma, x2, comma, x3, and so on, x, and so on, x. And this is what the functional relation is. The functional relation between the dependent and independent variables will be like if x is a dependent variable, x is function of f of x1, comma, x2, comma, x3, and so on, xn. Please note that all these independent variables are separated by comma here. Separated by comma, x1, comma, x2, comma, x3, comma, x4, and so on, xn. So you established the functional relationship between the dependent and independent variables involved in a physical phenomena. Based on the Rayleigh's method, this functional relationship can be converted into an exponential relation like this. An exponential relation. Thereby, you are now forming an exponential equation. What is this exponential equation? X is equal to, instead of keeping a functional relation, some constant c multiplied by x1 to the power small a into x2 to the power b into x3 to the power c, so on, into xn to the power n. This is what is the exponential equation which has been written out of the functional relationship. So the functional relationship, you have got all the dependent and independent variables. You have listed all the variables. You have listed all the variables and you established the functional relation. The moment the functional relation is established, like x is equal to function of x1, comma, x2, comma, x3, and so on, this can be converted into an exponential equation using this Rayleigh's method as x is equal to some constant c into x1 to the power a into x2 to the power b into x3 to the power c, and so on, into xn to the power n. So what is the change that has been made? All comma are being separated here in the case of functional relation, whereas here all the terms are now multiplied, x1 into x2 and so on. Further, each independent variable is raised to an exponent power a, b, c, and so on. You got the point? X is equal to function of x1, comma, x2, comma, x3. That is a functional relationship. In the case of the exponential relation, exponential equation, x is equal to some constant c into x1 to the power a. So x1 is the independent variable which is raised to power a, multiplied by x2 to the power b, multiplied by x3 to the power c, and so on, xn to the power n. This is what is called the exponential equation using Rayleigh's method. What you need to do in this exponential equation, you got now exponent variables a, b, c, and n are exponent variables. Exponent variables. Okay, so c is a dimensionless constant, and this constant may be determined by making use of the physical characteristics of the problem. Sometimes even from the experimentation also we'll be able to arrive at the value of c. And a, b, c, n, these are all the exponent variables. So this can be evaluated on the basis that the equation is dimensionally homogeneous. This exponential equation is considered to be the homogeneous equation, and treating this equation as homogeneous equation, we try to solve for the exponent variables a, b, c, and up to n. We try to solve for a, b, c, etc. up to n. What is that we are doing? We are doing that left-hand side and right-hand side, the dimensional formula is same. That is what is called dimensionally homogeneous equation. So the dimensionless parameters are then formed by grouping together the variables with like powers. That means we try to make a reverse operation by converting this exponential equation to a functional relationship. We will be able to establish a relation between the dependent and independent variables. Okay, we take a very simple small problem. Consider the problem of flow of a fluid through a small orifice. Flow of fluid through a small orifice, discharging freely into atmosphere under constant head. This is a very well-known concept which we know very well, by orifice, mouthpiece. When we have studied in fluid mechanics, you know what is orifice? Orifice is a small opening provided by the side or bottom of a tank to discharge the liquid freely into atmosphere. So you have a small opening provided. So this is a tank. In this tank, you have the liquid, say, up to this level, and there is a small opening provided, and this opening is called the orifice. This opening is called the orifice. Now, what we are trying to see, we try to analyze this problem, this discharge through the orifice, by making use of this mathematical technique, dimensional analysis. Already we analyzed this problem in our fluid mechanics by making use of applying the momentum equation, discharge continuity equation, and so on. You must have already derived it. The final form of equation also is very well known to us. What is that equation? Discharge through small orifice. Q is equal to CD into small a into square root of 2GH. So this is the equation that was derived by making use of the conventional approach. Now, using this mathematical technique also, we may arrive at it. So this is a small cylindrical tank. An opening is provided here, which acts as a orifice. So if we take a section for the same, we will be getting a small opening here. Through this opening, the liquid is discharging freely into atmosphere. So what are the dependent variables in this system, and what are the independent variables in this system? This is required to be known. The moment I say orifice, what is the size of the orifice? This is one physical parameter which may be independent variable, but what is the size? So that is the diameter of the orifice is required. Also, up to what level the water is available, the liquid is available. That means head over the orifice. Head over the orifice is required. The size of the orifice is required. Then what are the properties of the fluid which is discharging from this? Like what is the mass density? What is the dynamic viscosity of the fluid? And of course, where is this located? Acceleration due to gravity. All these are becoming the independent variables. What is the dependent variable? The discharge Q, which is required to be found. That means the discharge Q depends on the diameter of the orifice. Head over the constant head maintained here over the center of the orifice. Mass density of the fluid flowing through this orifice opening. Dynamic viscosity of the fluid flowing through this orifice. Acceleration due to gravity. So all these are the independent variables, and the discharge Q is a dependent variable which depends on this. So the discharge Q is assumed to depend on the variables like the diameter, head, mass density, viscosity, acceleration due to gravity G. So Q depends on dH rho mu G. Q depends on dH rho mu G. That means you will be able to establish a functional relation. The functional relation would be Q is equal to f of some function of mu comma rho comma d comma h comma g. All these independent variables are to be separated by comma in the case of functional relationship. Using Raleigh's method, the same thing can be converted into an exponential equation. The exponential equation would be Q is equal to some constant C into mu to the power A, exponent variable A, rho to the power B, into d to the power c into h to the power d into g to the power e. So what has been done now? We have done all the variables, the exponent variables, independent variables, which have been separated by comma in the functional relationship, have been brought into the exponential equation, and they have been made multiplied with one to the other by raising to the exponent variable powers a, b, c, d, e. A, B, C, D, E. Now, C is the constant. A, B, C, D, E are the exponent variables. Mu, rho, D, H, G are the parameters, are the independent variables. And Q is a dependent variable. So now we have established the exponential equation. What is the next step? You need to write the dimensional formula so that you will be able to solve by treating this entire exponential equation as dimensionally homogeneous equation. Solve for the exponent variables a, b, c, d, e. You need to solve for the exponent variables. So C is a dimensionless constant, and you need to solve for the exponent variables a, b, c, d, e, treating this equation as a dimensionally homogeneous equation. So to treat this as a dimensionally homogeneous equation and to substitute the dimensional formula of all the parameters here, you see mu, the viscosity, rho, the mass density, d, the diameter of the orifice, h, constant head over the center of the orifice, g, acceleration due to gravity. Similarly, on the right hand side, q, the discharge. For all these parameters, you need to write the dimensional formula in the Mld system. Dimensional formula in the Mld system. Take q first. Q is the discharge, volume rate of flow, volume per unit time, volume per unit time, meter cube per second. That means L cube divided by T. L is the linear, linear dimension, T is for time. So L cube by T, or L cube T to the power minus 1 on the left hand side. Similarly, on the right hand side, you have C, the constant. So since it is constant, its dimensional formula will be m power 0, L power 0, T power 0. Then mu, the dynamic viscosity. How do you get the dynamic viscosity? To get the dynamic viscosity, it is something like you can make use of the Newton's law of viscosity. Tau is equal to mu into du by dy. Or mu is equal to tau by du by dy. dv by dy or dou v by dou y is the velocity gradient. Tau, the shear stress, which is given to be the shear force divided by area. So mu will be equal to tau by dou v by dou y, or shear force per unit area divided by dou v by dou y. Shear force, it is once again a force, mass into acceleration, m into L T to the power minus 2, divided by area, square of a linear dimension, meter square, so L square, m L T to the power minus 2 divided by L square, divided by dou v by dou y, velocity gradient, that means velocity per unit length, velocity L T to the power minus 1 per unit length divided by L. So if you simplify this, you will be getting the dimensions of the viscosity as m L to the power minus 1, T to the power minus 1. Same thing we have used here. L to the power minus 1, T to the power minus 1. Similarly, for mass density, mass per unit volume, m is mass divided by meter cube. So L T to the power minus 2 kg per meter cube. M L to the power minus 3. M L to the power minus 3 mass density, mass per unit volume. Okay. Volume means it is a cube of a linear dimension, L cube. Since it is in the denominator L cube, when it is brought to the numerator, it is L to the power minus 3. Whole to the power B. Then D, the diameter. Diameter D, a linear dimension. So L. The dimension is L to the power C. Then H, the constant head, which is once again measured in meters. So the dimension is L. G, acceleration due to gravity. So meter per second square. L T to the power minus 2 to the power E. This is what writing the dimensions for the left hand side as well as right hand side of the exponential equation. Now what you need to do, you need to club all, Now you need to club all the parameters or the powers of the same terms. So for dimensional homogeneity, the exponents of each dimension on both sides of the equation must be identical. So on the left hand side you have L cubed t to the power minus 1. That means m power 0, L to the power 3, t to the power minus 1 is equal to, on the right hand side, you bring all m to the one side. M to the power, you have a here, m to the power b. So a plus b, m to the power a plus b. Similarly, L to the power minus a minus 3b plus c plus d plus e. T to the power, you have t at two places, minus a minus 2e. So on the left hand side, you have m power 0, L to the power 3, t to the power minus 1. On the right hand side, you have m power a plus b, L to the power 1 equation, t to the power another equation. Now, equate the powers of the similar terms. M to the power 0 here. Here, m to the power a plus b. So, equating the powers of the same similar terms on the left hand side and right hand side, a plus b must be equal to 0. Similarly, for L, on the right hand side, on the left hand side, you have 3. Here, minus a minus 3b plus c plus d plus e is equal to 3. T to the power minus 1, t to the power minus a minus 2e. So, comparing both, you are getting minus a minus 2e must be equal to minus 1. Now, you have got 3 equations, one for m, for L, and the other for t. You got now 3 equations. A plus b is equal to 0. Minus a minus 3b plus c plus d plus e is equal to 3. Minus a minus 2e is equal to minus 1. How many variables are there in these exponent variables? How many exponent variables are there in these 3 equations? A, B, C, D, E. 5 variables are there. How many equations? 3 equations are there. One for M and the other L and the for T. So 3 equations, 5 variables have to be solved. If the number of equations are equal to the number of unknown variables, then you can achieve the unique solution. Otherwise, if the number of equations are less than the number of variables, you will get infinite number of solutions. You will get infinite number of solutions, which means that you choose any 3 exponent variables and solve those 3 variables in terms of the remaining 2 variables. Because total 5 variables are there. Total 5 variables are there. A, B, C, D and E. So, you need to choose any 3 variables, solve these 3 variables in terms of the remaining 2 variables. Since there are 5 unknowns in 3 equations, 3 of the unknowns must be expressed in terms of the other 2, say A and D. That means what we are trying to see, B, C and E are solved in terms of A and D. Take equation number 1. A plus B is equal to 0. This is the equation that we have got. From A plus B equal to 0, B will be equal to minus A. Similarly, take the third equation. Minus A minus 2E is equal to minus 1. Or minus 2E equal to minus 1 plus A. Or E is equal to 1 minus A by 2. You have solved for B. You have solved for E in terms of A. Now take the second equation. Minus A minus 3B plus C plus D plus E is equal to 3. So, you have the value of A, which is directly A itself. The value of B is minus A. Substitute here. The value of E is equal to 1 minus A by 2. Substitute here. Solve for B. This can be solved for B in terms of D and A. So, B will be equal to 5 by 2 minus 3 by 2A minus D. Now, you have solved for 3 variables in terms of the remaining 2 variables. Substitute. You substitute these in our exponential equation. Our exponential equation is Q is equal to C into mu to the power A, rho to the power B, D to the power C, H to the power D, G to the power E. Substitute for all the variables what you have got now. A anyway is taken as A only, and B is equal to minus A. So, rho to the power B, rho to the power minus A. D to the power C, C that you have got as 5 by 2 minus 3 by 2A minus D into H to the power D itself, because we are solving in terms of A and D. G to the power E, E is half minus A by 2, 1 minus A by 2. Now separate all the exponent variables here. For example, if I have mu to the power A, rho to the power minus A, D to the power 5 by 2 into D to the power minus 3 by 2A into D to the power minus D, separate out. Separate out for all the exponent powers. Then try to group them together. What I have done here, d to the power 5 by 2. It does not contain any exponent variable. So brought to one place. Similarly, g to the power half, there is no exponent variable a or d. So bring here. So c into d to the power 5 by 2, g to the power half have been brought together into rho to the power a. All a's at one place. Rho to the power a, mu to the power a, rho to the power minus a, and d to the power minus 3 by 2 a. All three are with power a. Of course, one more. G also is there with minus a by 2. Then h to the power d. D to the power minus d. All d together. H to the power d, d to the power minus d may be written like h by d whole to the power d. H by d whole to the power d. Similarly, this term also. Mu to the power a, rho to the power minus a. So mu to the power a by rho d to the power 3 by 2, g power half to the power a. In other words, mu by rho d to the power 3 by 2, g power half whole to the power a. So mu by rho d to the power 3 by 2, g power half whole to the power a into h by d to the power d, and the remaining constant values, whatever you have got. So for the sake of convenience, for the sake of getting this in a very known form, what can be done here is that d to the power 2, d to the power half, and g to the power half are there. What is done here is multiply with h to the power half and divide with h to the power half. Divide with h to the power half. Accordingly, we will be getting in a very known form. Similarly, multiply and divide with pi by 2 into pi by 4 into root 2. Pi by 4 into root 2 here. Pi by 4 is taken here. And accordingly, you will be getting a root 2 gh pi by 4 d square may be taken to be a into root 2 gh into function of this. So the moment I say function, the power a should go away and you will be getting a comma. You will be getting a comma. All this is taken as the coefficient of discharge is CD. So C into A into root 2GH is the final usual form of the discharge equation through NRFIs, where CD, the coefficient of discharge, is function, some function F1, because F already we have used. So some other function F1 of mu by rho d to the power 3 by 2 g power half, comma h by d, comma h by d. Please note that both the terms become dimensionless, of course. Into A into root 2gh gives you the discharge equation through a small RFIs. So what we are trying to do here is, we are not applying the continuity equation at all. Also, we have not applied the momentum equation. But still, we have arrived at the required solution for the problem, that is the discharge through a small RFIs. A small RFIs connected to the tank. And what is required is, you need to identify what are the dependent variables, what are the independent variables, and what is their dimensional formula. If you know that, that is more than sufficient to derive this equation. We have not used any fluid mechanics concept. We have not used any fluid mechanics concept like momentum equation not applied, discharge equation not applied, continuity equation not applied. We have not understood any concept of the fluid mechanics, but still we have solved. So it is a mathematical solution for getting the solution for many fluid flow problems. So as compared to the discharge equation through a small RFIs, this appears to be a little lengthy and laborious at the moment. But when you start practicing fewer number of problems, definitely you will be able to find the ease that is available here. So wherever there is more and more complexity in applying the fluid flow fundamental equations like continuity equation, Bernoulli's equation, momentum equation, then if you try to attempt for solving such fluid flow problems, they become, the solution for that may be very laborious, sometimes very complex also, very complex also. In such cases, this mathematical technique will be highly useful. Because in this mathematical technique, we have been using a very set procedure. The set procedure is so simple: identify the dependent variable, identify all the independent variables, establish a functional relationship, form an exponential equation, treat that exponential equation as a dimensionally homogeneous equation, write the dimension formula for all the variables involved in that exponential equation, then group the powers of the like terms, and then solve for the exponent variables. Solve for the exponent variables. Convert this exponential equation into a functional relation. That means reverse it. Reverse it. You are establishing a equation. So this is the solution for the fluid flow problem, making use of the dimensional analysis technique. Say Raleigh's method. This method is the Raleigh's method. Okay. Just try to attempt for this problem, like the torque of a wheel of diameter d revolving at a speed n and fluid viscosity mu, mass density rho, is given by t is equal to rho d square and square into some function psi of mu by d square n. Use Raleigh's method. Also find the power p is equal to this. Okay, so this is the problem given. We follow the simple procedure as we have seen there. From this, you will be able to identify the torque is the dependent variable, and all other things are the independent variables like speed, kinematic viscosity, or the dynamic viscosity, and then the mass density rho, and then the diameter of the wheel, or they are the independent variables. Independent variables. So the functional relationship between the dependent and independent variables can be given to be T is function of rho, d, n, and nu. Right? The dimensional formula for all this. Rho, the mass density, ml to the power minus 3, d, the diameter L, and speed n, t to the power minus 1. Okay, and kinematic viscosity mu by rho, kinematic viscosity mu by rho, L square t to the power minus 1, and torque T will be equal to force multiplied by distance, ml t to the power minus 2 into the distance L, ml square t to the power minus 2. So T is equal to, you are now converting the functional relation into an exponential relation. C into rho to the power A, d to the power B, n to the power C, and mu to the power D. Now, write the dimensional formula for all these parameters. Group the terms, m power A, L to the power this equation, T to the power this equation. Equate the powers of the like terms. For m, left hand side 1, right hand side A. A is equal to 1. Similarly, minus 3A plus B plus 2D is equal to 2. Minus C minus D is equal to minus 2. So you have got 3 equations. Solve for these 3 equations, but you have 4 variables, A, B, C, D. 4 unknowns are there. So you need to solve 3 unknowns with one of the remaining unknown. So A is equal to 1, C is equal to 2 minus D, and B is equal to 5 minus 2D. Substitute those values here back. Rho to the power 1, D to the power B, 5 minus 2D, N to the power 2 minus D, mu to the power D. So separate out all the terms here. You have got C into rho D to the power 5 N square into 1 by N D square to the power D, mu to the power D. The moment you are reverting back to the functional relation from the exponential relation, these powers D, power exponent variables will go. Exponent variables will go. So into function of mu by N D square. The power P, of course, will be equal to task per second. So ml square 2 to the power minus 3. So accordingly, you got rho n cubed d to the power 5 into function of mu by N D square. As simple as this. Okay. So this is how the Raleigh's method. And we stop here at this stage. And tomorrow's class we see